Good morning, everyone, and welcome to this webinar organized by ESWET. My name is Aurélien Ballagny, and I have a great pleasure of being the moderator for today's event. Before saying a few words about the topic and our guests, please allow me to briefly introduce the association. So ESWET represents in Europe the manufacturers of waste energy technologies. So the companies involved in the design, building, maintenance, and refurbishment of waste energy plants. The main goal of ESWET is to raise awareness about the role of waste energy in the waste management chain. As a reminder, the role of waste energy primarily is to treat waste that is not suitable for recycling and would otherwise end up in landfills with long-term risk of pollution to soil, groundwater, air, including but not limited to methane emissions. We have currently 31 members that are among the main players globally. Thank you. So now about our event today, the topic of this webinar is pollution and waste to energy, myth or reality, ? And we believe this is a legitimate question, not only for you decision makers, but also for concerned citizens and for municipalities having to invest in solutions for the treatment of their non-recyclable waste. To answer the question of this webinar, we have with us today, I must say, a nice line of speakers, and I will start the introduction with Anita Matic. Anita Matic will give us a regulatory overview on the topic on behalf of the European Commission. Anita is well versed in this topic as a policy officer of the unit in charge of industry emission and safety at the Directorate General for the Environment. Anita, it is always a pleasure to have you with us at our events, so welcome. Then we have Leen de Bruycker, Technical Officer at CEWEP. Leen will introduce their latest report on dioxin emissions. So what is the concrete situation in waste to energy plants? Leen will tell us everything, and I look forward to your presentation. Then we also have the pleasure of welcoming Professor Lonati from the Polytechnic University of Milan. Professor Lonati will give us some perspective with a comparison between waste to energies emissions and pollution from road traffic. Professor Lonati, welcome. And for the last presentations, two engineers will cover the technologies involved in pollution prevention and emissions monitoring in waste to energy plants. For the first aspect, we welcome Rüdiger Margraf, member of the ESWET Technical Committee and Managing Director at LUEHR. We'll also have for the monitoring topic will be addressed by Aurélie Moll, also member of our Technical Committee and Technical Industry Manager for Carbon Capture, Utilization and Storage and Waste in Recycling at the company SIC. So welcome everyone, it's a pleasure to have you today for this event, and I think we can start the webinar with a presentation by Anita.
Good morning to everyone. Thanks a lot for the introduction. I would also like to thank ESWET for organizing this webinar and for having invited the Commission to participate. Next slide, please. In my today presentation, I will get a short overview of the legislative framework that applies to plants that incinerate waste. And the presentation will be concluded with a few words about the ID and the PRTR revision process. Next slide. The Industrial Emissions Directive is the main instrument that regulates emissions of pollutants from industrial installations at EU level. It has in its scope around 52,000 of the largest industrial installations, and including also plants that incinerate and co-incinerate waste. And you can see that waste sector accounts for around 20% of total number of the largest industrial installations that are under the ID scope. The Industrial Emissions Directive is based on an important principle, which is an integrated approach. That means that together with emissions to air and water, it also regulates other environmental aspects, such as waste generation, resource use, noise, odor prevention, etc. Although there is a significant decrease of emissions of pollutants that are regulated under the Industrial Emissions Directive, the IED installations still contribute in total to around 20% of total emissions to air, and to around 20% of total emissions to water, and to 40% of greenhouse gas emissions. The IED's integrated approach to prevention and control of pollution and environmental management has strong links with other European Green Deal policies, like, for example, waste, chemicals, energy, innovation, etc. And the current revision of the Industrial Emissions Directive aims to make it more consistent to other policies under the European Green Deal. Next slide, please. Thank you. The Industrial Emissions Directive and the European Pollution Release and Transfer Register Regulation are two complementary instruments. The EPRTR regulation establishes a database with data on annual mass emissions of pollutants to air, water, and waste transfers from installations that are under the IED at EU level and wider. The main objective of the EPRTR is to inform public on environmental data that also enables their participation in decision-making process. All this information that are reported to the EPRTR from industrial installations are available under the Industrial Emissions Portal. The portal now replaces the EPRTR website, and it's managed by the European Environmental Agency. In the portal, you can find various analyses of reported data, including also comparisons between specific pollutants, and for example, at sectoral level or at member states level, etc. Next slide, please. Waste sector has been regulated under the IED since decades. It has been strictly regulated, maybe more than any other sector. Chapter 4 and Annex 6 of the Industrial Emissions Directive provides minimum requirements for plants that incinerate waste. Those requirements are emission limit values, safety net, in a form of daily and half-hourly averages. Then the IED provides monitoring requirements, process conditions that have to be fulfilled. This is mainly related to minimum temperature and residence time to ensure destruction of harmful substances. And the IED also provides rules for assessment of compliance with emission limit values set out in the permit. Another chapter of the Industrial Emissions Directive, Chapter 2, obliges installations that are listed in Annex 1 of the Industrial Emissions Directive to apply best available techniques. And these best available techniques for waste incineration sector are described in a Commission implementing decision establishing vast conclusions for incineration of waste that was adopted and published in December 2019. This is a legally binding document, so BAT conclusions are legally binding documents, and permits must be updated within 4 years after publication. So that means by December 23. And after that date, emission limit values in permits must not exceed BAT associated emission levels from BAT conclusions. Derogation is possible, but only in specific and justified cases according to Article 15.4 of the IED. So only derogations from BAT associated emission levels from the BAT conclusions can be possible. Thank you. Next slide, please. This slide provides a summary of new requirements that are under the BAT conclusions in comparison with minimum requirements under the IED. So BAT conclusions contain BAT associated emission limit values for air and water emissions. These values are given in a range of emissions. And these levels are stricter than minimum requirements under the IED. And on that way, the level of environmental protection will be improved for pollutants that are regulated under the BAT conclusions. BAT conclusions also provide BAT-associated energy efficiency levels, and then it differentiates between levels for new and existing plants. There are also specific provisions in the BAT conclusions for the recovery of valuable materials from bottom ashes. It is important to mention that provisions that are related to monitoring are more demanded under the BAT conclusions. In particular, this is related to toxic and persistent organic pollutants, such as dioxins, furans, and PCBs. But conclusions also provides for improved sampling procedure for mercury and the dioxin, furans, and PCBs, and dioxins like PCBs that also cover other than normal operating conditions. There are also requirements under the BAT conclusions for periodic monitoring of other harmful and toxic substances. And BAT conclusions for continuously monitored pollutants requires sets only daily levels, daily ranges for BAT-associated emission levels. Next slide, please. I will conclude my presentation with the IED and EPRTR revision. This has been a long process, started at the beginning of 2020, and the current state of play is that we have finalized both impact assessments, and the Commission has adopted and published the both proposals 2 days ago. Next slide, please. The objective of the revision was to transform the IED and EPRTR into forward-looking legislation to combine the industrial transformation, but also to fulfill ambition under the European Green Deal and Zero Pollution Action Plan. The proposed amendments to the IED and DPRTR aim to enhance the IED effectiveness, to support innovation, to enable circular and resource efficient and less toxic production, but also to support decarbonization. And on top of this, we also, the new proposals are also widening the scope to ensure that both IED and DPRTR sectoral coverage is up to date. I would like just to highlight the few aspects that are now introduced by the new amendments that are related for increasing the ambition in permits to ensure that the whole range of BAT-associated emission levels is used. Then another important amendments is that that creates innovation center for industrial transformation and emission that inform on technological progress. Then setting energy efficiency requirements that will contribute. This will contribute to decarbonization. Then continuous monitor on uptake on innovation, and monitoring of improvement in the resource efficiency under an environmental management system. So with this, I would like to thank you for your attention, and I will be happy to answer later on any questions that you may have. And I give back the floor to the chair of this webinar.
Thank you very much, Anita. And given the legislative agenda with the recent proposal for the IED, I expect many questions for you with the Q&A, so sorry in advance. So about that, for the audience, after the presentation, we'll have half an hour of question and answers with the speakers who we have with us today. So do not hesitate to already send your question during the presentations. To send your questions, please make sure to use the Q&A button at the bottom of your screen and not the chat, because otherwise it will not be practical for us manage both. So please send us your question via the Q&A function. You can find it at the very bottom of your screen. It's simply written Q&A and it is there. So thank you, Anita. And now our next presentation is by Leen de Bruycker, Technical Officer at CEWEP. I give you the floor.
Yes, thank you. So hello, everyone. My name is Leen, and I will be presenting on behalf of CEWEP, which is the Confederation of European Waste-to-Energy Plants. I would also, of course, like to thank ESWET for the opportunity to take part in this webinar. And in this presentation, I will focus primarily on CEWEP's dioxin report, which was published in the beginning of March 2022. So next slide, please. Yes, so our report bears the title Dioxins and Waste-to-Energy Plants, State-of-the-Art, a European-wide overview of long-term analysis of dioxins in the surroundings of waste-to-energy plants, which is quite a long title. But dioxins and the waste-to-energy sector have long been associated with one another, so mainly because of the sector's historical contribution. And adding to that, the bioaccumulative nature of dioxins, it is no wonder that they are labeled persistent organic pollutants, or POPs for short. What this means is that they strongly resist biodegradation and can thus accumulate over time in the environment. CEWEP prepared this report to showcase the sector's efforts and current commitment to minimize dioxin emissions. It was based on an extensive data we received from our members around Europe. And in this way, it provides an in-depth assessment of the waste-to-energy sector's current monitoring practices of dioxins and furans. On maybe a short side note, if I use dioxins from now on, I'm referring to both dioxins and furans, but it's just easier if I just go for dioxins. So next slide, please. So I will first tackle our main takeaways from the report, and then subsequently we'll go a bit further into detail for each conclusion separately. So if you're not into any of the details, this is the slide for you to remember. But the main conclusions go as follows. So first, the European waste-to-energy sector is one of the most strictly regulated industries, as we have heard in the previous presentation, in terms of pollution, prevention, and control. And today, the waste-to-energy dioxin emissions account for less than 0.2% of the total industrial dioxin emissions. And thus, it must be taken into account that stringent limits for monitoring of dioxins are in place also during different operating stages. And second, regardless of specific measuring equipment, a well-managed European waste-to-energy plant emits extremely low concentrations of dioxins and furans, thanks to its sophisticated combustion control and pollution abatement system. And then lastly, which is also quite an important one, no correlation between dioxins measured in the environment and emissions at the stack are found regardless of periodic or continuous sampling. So next slide, so we can go a bit more into detail for the first conclusion. So as already mentioned, the sector has been long associated with dioxins, but since 1989, European waste-to-energy plants are subjected to specific stringent legislation to prevent and control pollution. And then afterwards, throughout the years, these requirements have been continuously tightened. And then in 2019, the waste incineration BET conclusions, as also previously mentioned in the previous presentation, went even further, and they set even more ambitious targets regarding dioxin emissions. And here it is also specified that emissions must be monitored during also other than normal operating conditions. And it is very clear that this has led to a great historical decline, as well as other sources of dioxin emissions becoming more prominent. And this can also be observed in the graph on the left, which is put together by the European Environmental Agency, where the waste-to-energy sector is included in the energy production label. It's colored red. It's maybe not very clear, but what is clear is that you see it very prominently in the beginning of the graph, and then it just later on, not so much. So their contribution has declined significantly. So next slide. This is to go a bit more into detail on the drastic historical decline with a specific case study, which is from Sweden. To dive straight into the numbers, here they went from more than 100 grams of dioxins emitted per year in the mid-1980s to less than 1 gram per year in 2015. And this is clearly illustrated by the green line on the graph. And whilst you have this information, you must also take into account that these low emission levels are still maintained, whilst the sector's capacity has been more than doubled. Other dioxin emission sources have become more prominent throughout the years. So if you take a look at the pie chart on the left, you can see the large share of households and then the industry, which is iron and steel production, but then also a waste category. Keep in mind that waste to energy is not included here, but in the energy production category. So waste here means open burning of waste and then other non-BAT compliant handling of waste, which has a very important contribution. And then the graph on the right focuses specifically on Denmark, but it just says the same thing, shows the same thing, that residential areas have a very high share. So next slide. So for the second conclusion, mentions the extremely low dioxin emissions due to the sophisticated combustion control and pollution abatement system. Simply put, this means that waste to energy plants have highly controlled and complex flue gas cleaning systems in place. And to illustrate this, you can see in the graph dioxin measurements before and after one step in the cleaning system in the graph. So orange is before, blue is after. It's quite clear that there is on average a 96% reduction for only one phase in the system. So it really is very well controlled. And these are measurements also taken in flue gas cleaning systems of a waste to energy plant in operation. Next slide. The conclusion also mentions that the low emissions are measured regardless of specific measuring equipment. And this means that similar emission patterns between periodic measurements and continuous sampling are found. On a side note, if you're not familiar with this, when applying periodic measurements of dioxins, the sampling is done over a short period of time, like 6 to 8 hours, and then continuous sampling is carried out over longer periods of time, ranging from 2 to 4 weeks. And these longer periods of time, when applying continuous sampling, can also happen to include conditions outside of normal operations, for example, startup or shutdown. And when looking at the comparison of the average of these, the measured dioxin emissions are not significantly higher. This means that the same results are thus obtained with either monitoring methods. Next slide. Then we have arrived already with the last conclusion, and this one reads that no correlation between dioxins measured in the environment and emissions at the stack, regardless of periodic or continuous sampling. So the part on the sampling we have already covered, but it is quite interesting to know that whilst environmental samples provide a value for the amount of dioxins measured in that sample, it does not necessarily determine the emission source, but more on that later, because this is a quite important point. And then furthermore, the report includes different examples of biomonitoring for dioxins executed by waste to energy plants. I will not go into detail on this, but it includes sampling of soil, sampling of existing vegetation, or vegetation grown specifically for the purpose. Next slide. Okay, here I want to go a bit more into detail because it's quite an important point. So if we go back to the challenging task of identifying the emission source, it must be noted that it's not possible to guarantee the source of dioxin emissions solely based on the levels in biomarkers. Plus the pollutant concentrations found in the sample can originate from both recent sources and then also historical pollution, as dioxins accumulate in the environment over time. So for some processes, it is actually possible to identify the source based on congener patterns, and congeners are chemical compounds, or simply put, building blocks that are related to each other and can give more information on the origin of the chemical compounds. So as dioxins cover a group of more than 200 compounds, you can set up a congener pattern for a sample, but also for an emission measurement. And if these two match, you know the source. But it's a very great argument that this only works if the emissions from a certain industrial process have a specific congening pattern. And this is the case, for example, for pulp bleaching. But for incineration of municipal waste, this is, however, not the case. And to go even further, all combustion processes show similar congening patterns, regardless of the input waste. It also similar patterns have been found in the metallurgic industrial processes. So the pattern on the right shows that it doesn't differ significantly from the pattern for traffic emissions. So how do we find the emission source? So the only way, if you find elevated amounts of dioxins in a sample, is to compare it with a framework of measurements from all possible sources in the surroundings, including the measurements that you have taken at the stack at the waste to energy plant. So next slide. This is my last slide, but it's just a quick overview of the direct emissions that are directly linked for monitoring, and then the environmental samples or air quality monitoring, where you're unsure how to identify the emission source. And it's a bit wrapped up at the end, but I think that is it for me. So thank you for your attention. And if there are any more questions, I'll be happy to answer them later on.
Professor Lonati, if it's okay for you, I will ask you to start your presentation and we'll give the floor back to Leen later. Thank you.
Okay. Can you hear me? It's okay?
Perfectly, yes, no problem.
Okay. Thank you, everybody. Good morning. And thanks to the organizer for inviting me to give this speech on the subject you can see on this title. Next, please. Actually, in my presentation, I will touch some points, and mainly the reason for public concerns on WTE plants, and I will present the results of a couple of case studies we had on the impact of the emission of this kind of plants on air quality. Next, please. So I think that all of you are aware of the different kind of concern of public concerns against WTE plants. So I would like to stress the point of awareness on risk that sometimes is not so clear in public opinion. So maybe people is more keen to be afraid of some things like WTE plants emissions than other common activities that we have, like road traffic or domestic heating, namely when we have biomass burning. Next, please. And I will just show you some outcomes of a couple of studies we had, 2 case studies we had in Northern Italy. These studies had a common goal that was to assess the impact, the real impact of the plant on local air quality. They shared common methods, namely from the modeling standpoint, from the dispersion modeling standpoint, we use CalPath model. And the other point, the other important point we had was that we based our simulation on real emission data taken from the continuous emission monitoring systems. And in these 2 case studies, we had 2 different goals. In the case 1, and I'm showing you, was the study was intended to compare the impact of the plant emissions with local road traffic emissions. So it was just only simulation exercise, let's say. And in the case 2, the idea was to compare the estimated contribution of the plant emission through modeling with monitoring data in order to have some idea of the relative contribution of the plant emissions to the actual air quality conditions. I will just go very fast on the results, but if you want to have detail, all these studies have been published. They are on open access journals, so you can have a look and find all the details you may be interested to. Next, please. Case study was for Desio plant, and the interesting thing was where we have been comparing the state, the impact of the plant before and after the revamping of the plant that occurred in 2016, with namely the introduction of the SCR unit for NOx control. together with an increase in incineration capacity. Next, please. The plant is located north of Milan in the Lombardy region. As I was mentioning, we took data from the CM system, and of course, for those pollutants that are routinely measured, PM10 and NOx, whereas we relied on the monthly average concentration data for from discontinuous sampling for dioxins. And we had simulation for calendar year 2016. Next, please. Here you can see that the revamping of the plant resulted in a decrease of emissions in average and also in absolute terms, in maximum levels of emissions from scenario A to scenario B, except for PM10, because we had an increase in the waste throughput. So there was this mismatch between increased emissions and controlling that was not fostered because the intervention was focused on NOx. Next, please. Now here you can see the distribution, the contour line showing the distribution of concentration levels for, this is for NO2, okay? But if you look at the numbers on the right side, you see that the maximum expected contribution for NO2 was just some 10 to the minus 2 of micrograms cubic meter, 10 to the minus 4 for PM10 micrograms cubic meter, and was in the 10 to the minus 4 femtograms for dioxins. Okay, and you see also the impact on the urban area, which was a little bit far from the point of the maximum fallout. In the final line, you can see also the air quality limit. So you see that there are orders of magnitude in difference between air quality limit and the contribution of the plant for NO2 on annual basis. By the way, you also can see that for NO2, the annual average concentration was exceeding the air quality limit because it was 46 versus 40. So we were in a polluted area, and it's well known that the Po Valley is not so clean from this standpoint. Next, please. The other goal of the plant was to compare the emissions, the impact of the plant with local traffic. So we had to choose some main roads crossing the municipality where the plant is located. They're the red lines. This means national roads, regional roads with high traffic roads, but overall account for about 70% of the total traffic emission within the municipality. Of course, we are not taking into account what comes from the other municipalities. We had a dedicated study for traffic flows. We relied on emission factors for PM10, NO2, and also for dioxins, and for different kind of vehicles, cars, light duty and heavy duty vehicles. Next, we run the model, and here you can see the contour plots for, this is for NO2 and this is for NO2, okay, data are also reported for PM10. You see that the impact of the road traffic is in the order of dozens of micrograms per cubic meter in the maximum point, in maximum fallout point, whereas in the urban area is in the order of, let's say, some micrograms cubic meters compared to 100 times lower contribution from the waste to energy plant. And is the same, or even more in the case of PM10, because you see that the factor, the ratio is 10 to the minus 4 in the case of PM10. Next, please. So, okay, here you can see the time pattern of daily average concentration for NO2 and for PM10. You see the monitoring data in the blue, and the pinkish is the traffic, and almost you cannot see the contribution. There is the contribution. There are small bars, but practically you cannot see the contribution of the plant emissions, both for NO2 and PM10. Next. So just to summarize the conclusion from this first study, okay, we had that the intervention, the ramping of the plant resulting in a positive effect in terms of reduction of emissions and also reduction in specific, I mean, per ton of waste burned. Okay, so not only in terms of concentration, but in terms of efficiency of the process. And we also saw that the impact, the contribution of the plant to the overall air quality is very low, and it's very low also in relative terms compared to local traffic. And when I say very low, I'm dealing with orders of magnitude. And this not only for the criteria pollutants, but also for organic and inorganic. We also investigated the case of cadmium, which is not shown here, together with dioxins. But I mean, we had the same results in terms of relative contribution in comparative terms. Next. The second was for a plant in the Veneto region, close to the mountain, with state of the art, okay, equipped with SCR and the traditional dry treatment line, okay, on 3 separate combustion lines, with a throughput of about 230 tons per day of waste. Next. We had the same methods, okay. We relied on data, on meteorological data. Actually, it was not a real calendar year because we were in between 2018 and 2019, because this was requested by local authorities. We also had we took data from routinary monitoring data for PCDDF and toxic elements. Next. Discontinuous sampling, and we ran some statistical analysis in order to, this is for dioxins, for example, to have a proper description of the real emission condition for these kind of pollutants. Of course, there is some variability, so we wanted to investigate this, not just to take one single value, but to make some deeper inference. Next. We had monitoring data that came from institutional monitoring run by the local environmental agency for both criteria pollutants, continuous and periodic sampling, daily samples throughout the year. Let's say about 60 to 70 daily samples over the entire year, the entire period, study period, which is actually a year. And also we had data from dedicated monitoring campaigns that was we perform for the managing company of the plant, and some other campaigns run by ARPA, which is the local environmental agency. And these campaigns were focused on elements, toxic elements, benzopyrene, dioxins, and furans, and also mercury. I will not show that, but also we had some total gaseous mercury monitoring. Next. Okay, this is the impact. The impact of the plant was very small. I mean, not small. I would say the impact area was very close to the plant because the stack was not very tall. It's about 50 meters. Okay, so the impact was mostly in a 2 per 2 kilometers area from the plant. But we'd like to raise your attention on the right side of the slide, where you have on top the range of the time pattern of the observations, so monitoring data for NO2 annual hourly data, and below you have model results. So you see that the range is 0 to 120 for observation, and 0 to 6 for model results, and 6 is, I mean, most of the time we are below 2. So once again, the contribution for this, for NO2, was very small, is very small. Next. The same for PM10, or even greater, smaller, let's say, greater the difference and smaller the contribution of the plant. we are maximum in the terms of 0.01 micron cubic meter, and in comparison, we are normally in the 20 to 40 micron cubic meter range for ambient air, with some peaks up to 100 in given critical conditions. So we have some further confirmation that the impact of the plant is very small, as we saw for in the previous case. Next, please. Some interesting data for organic and inorganic trace pollutants. I just chose some of them. The left bar is, you see seasonal data. Okay, first of all, comparison for summer and winter period. The left bar is the range for measured values. The right bar is the range for modeled values based on daily samples. Okay, so you see that in all the case, model simulation are well below the observation data. And in some cases, there are really big difference. Look, for example, to benzoapyrene in the winter period, when we have several order of magnitude difference between observed values and estimated contribution of the plant. And this is also true for dioxin. See that there are at least 2 orders of magnitude difference. Next. So once again, we have that the contribution of the plant is really marginal compared to ambient air level. And actually, we have that it's the complex of all the activities in the area with residential biomass burning, but also road transport and some industrial processes activities that are in that location, that are the most significant contributors to pollution levels at the local scale. And I would like to raise your attention on what I call provocatory question, that came out of the discussion with the local agency for air quality. And the question is, well, if you want, does it make sense to have short monitoring campaign, just snapshots of air quality as far as dioxins and some toxic elements are concerned? Or if you want to be more formal, do periodic monitoring campaigns provide suitable information to really assess the impact of the plant when you are in a complex area with many sources, different sources? Well, we had some debate about that, and I will try to just make a suggestion in my final slide with the overall conclusion. And the conclusion is that maybe in the last line, I would say the last bullet point, monitoring coupled with modeling may be a good tool to assess and to keep control, or to have information about the real impact of the plant. I would like to mention the fact that in our simulation, we took continuous monitoring system data, and as they are, so there was no further processing, as sometimes it happens, in order to not to consider transitory periods or whatever you want. So we took all data measured and we modeled that, okay? And in order to try to pick to really assess the real, or if not the real, the most close to the real impact of the plant. And the final point is that, of course, we had to, the plant we studied in our case studies were not very big plants, but they were state-of-the-art, recently revamped with state-of-the-art technology, according to best available technologies address. Okay. I thank you for your attention. I will be very pleased to answer your questions, if any. So, and thanks again to the organizer for asking me to be here with you. Goodbye.
Not yet. We will see you for the Q&A.
Goodbye for the moment. Okay.
But thank you for this presentation. It was very interesting. In fact, you answered already many questions we already have for the Q&A, but I will forward them later. So for our next presentation, you mentioned flue gas cleaning system, and so to tell us more about it, we have Rüdiger. And Rüdiger, the floor is yours.
So, hope you can see it now. Yeah, good morning, everybody. Topic of my presentation is the flue gas treatment for waste to energy plants, the use technologies, and I want to start with the classification of pollutants and introduction of separation technologies, followed by some execution examples with measured values and a brief summary. On this slide, you see all the pollutants and compounds which have to be removed from the off-gas from waste to energy plants. You see it here in this left-hand column, the pollutants, and here in these two yellow ones, you see the range of limit values to be achieved with a flue gas treatment system. You can classify all these compounds in, let's say, 4 or 5 classes. The first part of flue gas treatment starts already in the combustion zone with oxidizing CO and organic compounds, and all the other classes are mainly removed in a flue gas treatment downstream of the waste to energy plant, of the waste recovery boiler, or even inside of the waste recovery boiler, heat recovery boiler, sorry. So the first class are the pollutants in solid form. This is fly ash, heavy metals in solid form. Then we have pollutants in gaseous form. That's the acid components, HF, HCl, SO2. These compounds are removed by adding an additive, which gives a chemical reaction, and you form salts, which you can then easily remove in solid form. The other group of further gas pollutants are mainly mercury and PCDD, PCDF. This for this you add an additive with site-specific surface in the range of 300 up to more than 1,000 square meters per gram. You fix it in these additives and can remove it from the gas. And last but not least, you have the NOx, which will be reduced to N2. What are the technologies behind? If you look first for the pollutants in solid form, mainly used is a back filter, or also called fabric filter. The reason is that this has, compared to other technologies, the highest efficiency. So you see in this diagram here on the top, the back filter compared with the red line here for the electrostatic precipitators, and wet systems with this blue line here. As already mentioned, you can remove the pollutants in solid form, but as well also pollutants in gaseous form. If you convert these pollutants to solid form, as you do for this sorption processes. Here you have different options. The first one is a dry sorption process using sodium bicarbonate. This is baking powder for the acid and active carbon for mercury and PCDD, PCDF. It consists of a reaction chamber where you introduce the additives, a filter, and a multiple recirculation. Second option you have is a conditioned dry system. Instead of sodium bicarbonate, here you use hydrated lime. You see more or less the same scheme. The reaction chamber where you introduce the two additives, the back filter, multiple recirculation. The difference is that you moisture a little bit, recirculated particles to improve the efficiency. Last but not least, you have, of course, the option of a wet system, wet scrubber based on sodium hydroxide or even limestone. Last group are the NOx, which has to be reduced to N2. This you do with injecting of ammonia. You have two options. The first one is to do it in the combustion chamber at hot temperatures in a selective non-catalytic reduction, or the other option is to do it within the flue gas treatment system downstream of heat recovery boiler, where you need then in the temperature range of 200 to 240 degree a catalyst system to support the reaction. These are the technologies you have available, and now it is a target to combine these technologies for a high efficient flue gas treatment for waste to energy plant. I selected 4 examples. The first one is SNCR technology with conditioned dry sorption, means here lime and active carbon. This is a plant in Germany, and on the right-hand side, you see the some part from the emission report from the year 2017. In the first line here, you see the measured values, mainly continuous measured values, and here the limit values. What you can see as well demonstrated in this comparison with percentage range, the high efficiency of the flue gas treatment system. I have here for 4 of these compounds also the monthly concentrations for SO2, HCl, mercury, and also for particulate matter. And what you can see is that there are variations over the months of the year, but all the values are far below the requested emission limit values. I added here from this report as well the dioxin measurement. Second example is an SNCR technology with a dry sorption. Means usage of sodium bicarbonate and activated carbon. Also here, an emission report from 2017. It's a plant with 3 lines. And as well here, you see in this part, all the continuous measured values, and here the values measured by sampling periodically. And if we look, for example, for this dioxin or the heavy metals, they are all far below this requested emission limit values. Third example is a little bit more complex plant. It consists of a conditioned dry system followed by SCR and a polishing dry stage using in both stages lime. And this is a plant in also in Germany. You see here the conditioned dry system. You see here the SCR and here the polishing filter stage, an extract of the emission report from 2018. Again, you see that all values are far below and within this range specified in the new waste incineration ref. Same for these compounds which are measured by sampling. Last but not least, one more example, and this is a combination of SNCR, conditioned dry system, and a wet scrubber. This is a very common combination of technologies used in north part of Europe, because you can here in the last stage, the polishing scrubber, you can remove highly efficient the remaining HCl and SO2, the acids, and this in combination also with heat recovery, because you can use the condensing heat generated here in this water of the scrubber, in the water loop of the scrubber, and give it to district heating. This gives you a very high energy efficiency as well. Here, one example of a plant in Finland. And you see here, for example, for HCl, SO2, extremely low values. A very brief summary. There are several different technologies available to remove pollutants. And these technologies are listed in the waste incineration graph as BAT. All these combinations of technologies in operation reliably fulfill today's and future requirements, including, and that could be seen in all these reference examples, sufficient safety margin. The selection of technologies is made depending on the application. Two of these considered factors are the fuel composition, energy efficiency, and last but not least, for the most of the pollutants, we have in the meantime continuous emission monitoring systems, which allow to monitor the efficiency of the flue gas treatment systems. With that, I'm at the end of my presentation. Thank you for your attention.
Thank you very much, Rüdiger. We were able to catch up actually, so thank you very much for being brief. And now about monitoring, I give the floor to Aurélie to tell us more about the monitoring technology.
Thank you. Good morning, everyone. So yes, my name is Aurélie Moll, and I will present you the monitoring technology as well as data evaluation for the emission of waste to energy plants. So first, we have seen it before. The waste to energy sector is one of the most strictly regulated sector for the emission. And generally in Europe, the industrial emissions are regulated by directive and standards. And we have especially now the IED, which is the Industrial Emissions Directive, that combined a total of 7 directives. Under these directives, we have the WID, which is the Waste Incineration Directive. And the IED is the main instrument regulating the pollutants emissions from industrial plants, and here especially regarding waste to energy plants. And this regulation are improved and revised in order to be based on the best available techniques. On the right-hand side, we see the BREF. We have seen it before as well. So the BREF are the best available techniques reference documents. So we have a different BREF, and we will have a look on the incineration part, which was revised in 2019. Very important is that the bad conclusion from the BREF are now legally binding to set the permit conditions for waste to energy plants. Additionally, there are related standards for the quality assurance and the certification of AMS. The AMS are the automated measuring systems. Next slide, please. So this is an overview about the battles from the BREF waste incineration. We have seen it before already, so I will not go in detail. But the battles are, as said before, legally binding to set the emission limit value for the waste to energy plant within the permits. We see that there are several components with very low levels that must be continuously monitored or with periodic measurement, depending on the components. Next slide, please. So waste to energy plants are controlled using a continuous monitoring system that can be used either on the raw gas side to control and optimize the flue gas treatment of the waste to energy plants, or for automated monitoring system to control the emission levels and the compliance to the emission limit value from required by the European regulations. Next slide. What we understand under AMS, the AMS are all the gas analyzers or flow meters that are necessary to control all the parameters required by the IED and BREF for the emission of waste to energy. On the next slide, we will see a typical, AMS, which is which measures, which stores, evaluates, and reports all the required values from the emission. So here we see a multi-component analyzer that can measure simultaneously and continuously several parameters. Here we have 10 parameters. We can have an analyzer to measure the total mercury content as well continuously when required, flow meter, dust analyzer, some sensors like temperature and pressure, which are used as reference values for calculations, and at least a data acquisition and handling system to provide all the required data evaluation and storage for the continuous control of the emission limit values compliance, and of course for the reporting to the authorities. So we have seen that there are related standards to the IED for the quality assurance and the certification of AMS. Here we have the overview about the quality assurance systematic from the standard EN 14181. So first, it must be ensured that the AMS is suitable for continuous emission monitoring. So each AMS must be certified according to the standard EN 15267 part 3, which is related to performance criteria and test procedures. The compliance is summarized within a Qual 1 certificate. So after that, and after installation and commissioning, it must be ensured that the AMS is set correctly. For this, a kind of calibration is realized. This is the so-called Qual 2. The Qual 2 is done by accredited laboratories to check the calibration. And during the Qual 2, 15 comparative measurements are taken by using a standard reference method, and a calibration curve is created. This Qual 2 must be repeated each 3 years for waste to energy plant. So after this calibration, and during 1 year, we have an ongoing quality assurance with zero check and span check. This is the Qual 3. And this Qual 3 is under the responsibility of the plant's operators. It is done according to the supplier instruction and the maintenance interval that have been defined during the certification process of the AMS. So after this, it must be ensured that the AMS stays working correctly. So there again, there is another test. This is the AST, annual surveillance test, again realized by accredited laboratory to check the linearity of the AMS and the calibration. Next slide, please. So here we see the interconnection between the directives and standard, and especially the quality assurance standard EN 14181, which is used by the IED and on site for the ongoing quality assurance with the Qual 3 check, and on the other side for the type approval of each AMS with the Qual 1 certificates, and of course for the ongoing check like Qual 2 or AST that are done via accredited labs. Next slide. So we have seen before that the AMS must been certified according to EN 15267 part 3. And this certification is done by certified bodies, for example, the TÜV in Germany or the CSI group testing in UK. And each certificate are available on the respective website. So here on qual1.de for the TÜV certificate or qual1 certificates, and here on the CSI group UK.org for the MCERT certificates. Next slide, please. Here you have an overview about the performance criteria that must be fulfilled by all analyzers that are used for AMS. The certification test is realized in 2 steps. 1 step under laboratory conditions and 1 step under field conditions. Some of the criteria are the response time from the entire AMS. That means not only the analyzer, but also the measuring gas line or the sample gas filters for extractive analyzers. The repeatability with standard deviation at 0 and span point, the linearity of the analyzers, the 0 and span drift, and the influence of several parameters is also tested with a limit that must be fulfilled. That's the case for the ambient temperature, sample gas pressure, sample gas flow, voltage variations, or vibrations. And all this performance criteria ensures that the AMS is working perfectly with a good accuracy of the measurement independently of the site conditions. Next slide, please. So we have seen before that the certification as well as CAL2 and AST must be done by accredited laboratories. And this accreditation is done according to European standard, the EN ISO IEC 17025, which is related to the general requirements for the competence of testing and calibration laboratories. Next slide. So I come to my summary. We can say that the long-term stable low emissions from waste to energy plants are ensured by the continuous monitoring and reporting of the emission done with certified AMS, with regulatory reporting to the authorities and the continuous data acquisition of the emission values, of course, with the application of European regulation and especially the waste incineration brief with the legally binding BAT conclusions, with the quality insurance of the AMS, which is done according to European standards. So you have compliant hardware setup, compliant factory calibration, reliable on-site calibration, and of course an ongoing quality check during the operation. So at least only accredited laboratories are allowed to do the certification and the Qual2 test or AST. And all of the steps ensures the reliability and the transparency on the low emission from the waste to energy plant in Europe. Thank you for your attention.
Thank you very much, Aurélie, and I'm afraid that after I kept repeating we need to stick to a timeline, I made you all rush your presentations because now we are ahead of schedule. But so anyway, thank you very much, everyone, for these interesting presentations. Now we have the opportunity of starting a Q&A with the audience, and we have many questions. So I will ask the speakers to turn on their cameras and microphones, if possible, at least when you take the floor. So we have a lot of questions. I would prefer we address them orally, but if at some point you see that in the next 10 minutes we will not have time to address everything, do not hesitate as speakers to answer them in writing. Feel free. So we have first maybe a simple question, asking for a black and white answer. Is incineration adding to air pollution or not? Capital letter, yes, no question. So I think that Professor Lonati, you addressed it in your final slide, but maybe you can go through it again, and maybe after that, Leen can also address the question. I mean, what would be the alternative, for instance, in terms of pollution, if those waste went to landfill, for instance? So, Professor Lonati, if you want to take this question.
Of course, we have every, I mean, anthropogenic activity is responsible for emissions. Okay, this is obvious. Okay, so we have a contribution. The point is that the contribution we have from waste to energy plant is when these plants are well managed, are state of the art, is small compared with all the other activities. This is the point. It's obvious that if you are in the desert and there is the only wet plant, wet plant will be the main factor affecting the quality of air, the quality of soil due to deposition and so on. But unfortunately, we live in our region in very crowded areas. So we have plenty of sources that give contribution. And in relative terms, waste to energy plants are not the leaders for that. This is the point. And even for those pollutants that are strongly associated to waste to energy plant, like dioxins, okay? You know that in Lombardy, due to the Seveso accident, there is much concern about dioxins among public opinion. Everybody is aware of dioxins. But I mean, there are many other sources of dioxins that give contribution and give even larger contribution. Most of these sources are uncontrolled, whereas waste to energy plants are controlled. This is the reason why I stress the point that well-managed publicity of the monitoring data and open, I mean, the manager should be open-minded towards population to make them really understand what they have to face when they have a plant nearby.
Leen, do you want? Oops, there is an echo. Sorry. Leen, do you want to add something, or someone else?
Well, I think Professor Lonati already said it very clearly, and I absolutely agree. I just also want to stress that indeed, if we have to look for alternative waste treatment methods for residual waste that cannot be recycled, the alternative is landfill, and the contribution to air pollution would be far greater than, for example, the highly controlled and BAT compliant waste incineration, waste to energy plants. So I completely agree with what was previously said.
Thank you. About that, I have a question maybe for you, Anita. Since we are talking about landfills and with the revision, the new proposal for VAD, what would be the timeline for BATs on landfills?
Yes, thanks a lot for this question. Yes, the new proposal proposes amendments to the landfill directive that currently applies to landfill. In principle, landfills are subject of the Annex 1 of the IED, but however, best available techniques for the landfills are currently described in the landfill directive, which is the old one. And we propose with new amendments to amend this landfill directive in a way that in the future we will have adopted BAT conclusions on landfills. In this moment, I'm not able to tell you exact date for this, because the proposal needs to be now, we are now in the next stage we're going to negotiations, interinstitutional negotiations that will take some time. So the proposal we expect will be finally adopted somewhere in 2003. So after that, we will update also the IPPC Bureau work program, and of course this will be also, as always, discussed in the forum with the stakeholders, and everybody will be informed when these BAT conclusions, when we will start to draft these BAT conclusions.
Thank you. So we have a lot of questions, so I'm trying not to be lost in the flow. I will give another question for Leen, and after that I will have some for Aurélie and Rüdiger about the monitoring and continuous monitoring. Question to Leen. So if waste energy emissions are in the energy category, then we should show these, right? Otherwise, we are comparing pears to apples. The absolute emissions of waste incineration are significant, yet constantly hidden, as the industry prefers to refer to not their category. So first, I must say, I don't know if anyone here has ever tried to have a discussion with Eurostat, but yeah. we are not responsible for their statistical choice, and definitely not trying to hide anything. Leen?
No, definitely not. That is also why we actually wrote the dioxin report, to have a bit more transparency and to have it maybe all in one place, so it's easy accessible as well. And it's publicly available, so if you would like to inform yourself, you can always go and find it online. But I think you're referring to the graphs in the sources slides, but these graphs indeed were to illustrate the overall shares of different dioxin emissions sources, and here they are from a report by the European Environmental Agency, and we are labeled under the energy production. It was not our choice, but I think it's not a bad one either. So it is also important, I think, to make a distinction between non-BAT compliant handling of waste and state-of-the-art waste-to-energy plants who comply with the strict regulation. And then if you want more hard numbers, I can refer you to our dioxin report, which includes several nationwide studies providing exact figures of yearly emissions. And as also I recall in my presentation, the Swedish example was that there is less than 1 gram per year emitted. So I think that is already a hard evidence. But other than that, I think it is still also important to consider also sources, whether they are industrial or not. I hope that kind of answers the question.
I sure hope so. Thank you very much. Then we have again, I will try to switch a bit, because it's also the questions by the same people, but then I will switch. We have a question that maybe can be answered by Aurélie, Rüdiger, or Leen. I mean, I'll let you choose who will answer it. The figures on dioxins presented are based on the EPRTR, so the register, and not on long-term monitoring. I will make it short. All measurements are announced in advance, so please, how accurate are those measurements? The recent report on the incinerator in Paris raises this important alarm. So if I may, about the report in Paris, I will refer to the answer by the French Minister for the Environment, former Green, saying that the report has many flaws, and including that it can come from many sources of pollution, and sometimes even pollution decades ago. I will put the link in the answer, but Aurélie or Leen, do you want to take this answer?
You can go ahead.
So we don't have long-term monitoring. How accurate are the measurements actually?
So is the question that there is no long-term monitoring in place, or?
Yes, the figures on dioxins presented are based on the EPRTR, not on long-term monitoring. All measurements are announced in advance. How accurate are those measurements?
So I'm not sure if I have too many knowledge about it, but I can say that the waste energy plants, some have long-term monitoring in place. And again, it doesn't show a very big difference with periodic monitoring, which are still very extremely low emission levels. And that is something I can add, but I don't know if it answers the question completely.
Yeah, I can also add something about it. Regarding the monitoring of dioxin, there is in case semi-continuous monitoring for dioxin. That means that there is a sampler that is installed at the stack, and the gas is extracted and stored, or the dioxin are stored within a cartridge, and this cartridge is exchanged and analyzed under a laboratory each 4 weeks. So this is a kind of continuous monitoring, but based on the 4 weeks period. And there is countries like France, for example, that are using this system already.
That is a better and more technical answer in mind. So
I can add, in our study, in the case 1, we relied on continuous sampling data for dioxins, and actually had monthly average values for the emissions, for the concentration, for the stack concentration, and therefore for the emissions.
Thank you. Then we have again a technical question, but I think it's because of the topic we are dealing with today. How did activated carbon work in the reduction of PCDDF? Maybe this question is for Rüdiger.
Yeah, the PCDF is fixed in this active carbon. Active carbon is an additive with very high specific surface, which is yeah, in the range starting with 300, 350 square meters per gram up to more than 1,000 square meters per gram. And it is fixed in this carbon. The process is called adsorption. Same with the mercury. And with that, you can remove it in a back filter. And it is safely stored in this carbon.
Thank you. So at this point among the speakers, if you spot a question that you believe you want to answer and I have not addressed already, you can take the floor and tell us about it, or just answer in writing. We have about 20 questions left, so I'm going through them. Yes.
Sorry, I see one question that is addressed to me. Perhaps I can answer it already.
Go on.
How do you measure carbon isotope ratios for determining fossil biogenic content of the CO2? So first, this is not required currently by regulation, but there are already some systems under development or already tested to do it. This is the same principle like for the semi-continuous monitoring of dioxin. So you have a sampler, cartridge, and this cartridge must be analyzed in laboratory to determine the C14 content of the gas.
Thank you. Then we have also a lot of questions related to biomonitoring, and I know that Leen, you had to rush earlier during your presentation, and so I just want to make sure you have maybe more time to explain yourself. So basically, we have many questions about what is it about, and saying yes, it is possible to identify the source of pollutants. You have to look at the congeners dioxins and so on and so on. So could you please tell us a bit more about it?
Yeah, of course. So first, to explain, biomonitoring is taking samples of the environment around either waste-to-energy plants or other possible dioxin sources, and then examining those samples renders an amount or a concentration of dioxins or other pollutants that are present within that sample. Which is, of course, a useful thing to do to know the levels and the background levels, for example, in the environment. But it must also be noted that this is not a guarantee to find the emission source. And to answer the question on the congener patterns, to find the source, is that you can indeed look at the congener dioxins to find the source. But if, as said in my presentation, they are very similar to congener patterns for other processes, it is not possible to exclude the other sources. And there are only quite a few very specific processes for which very specific congener patterns are available. So it is a very, very challenging task. So, but if you find a certain concentration of dioxins in an environmental sample, it indicates, as I said, elevated dioxin levels in the environment. So the only way to make sure it is to compare it with the dioxin measurements taken at the stack of the waste to energy plant. And then, of course, all other possible sources within the environment. And also, I would like to note for environmental samples, which is a bit tricky, is that the factor of historical pollution must also be taken into account. As waste to energy plants, they have often been standing for a long time in the same place. And we know before we knew about the dioxin contribution, you can still find traces of that period of time. And often they are in more industrial areas, and if not close to residential areas, we also already know that these also have a large share of dioxin emissions, and which is also very important, as seen in Professor Lonati's research, is that proximity to busy highways is also a very prominent dioxin source. And all of these will be measured in samples you take from the environment. I think, yeah.
Thank you. Do you want to add anything else among the speakers? No, I mean, it was already a very comprehensive answer, so I think there is nothing else to say. We have a question. We are talking about thresholds and rules and technologies applied in Europe, but we have a question about it, saying, can the same monitoring, evaluation and tech development be said about developing countries? And if not, how to counter this, since there are also many waste to energy plants in developing countries? Who wants to take this answer? This question, sorry. It's a tricky one, huh? So.
I can say that I have no experience about studies developed by our group in developing countries, unfortunately. And the point is about technology, control technology. It's well known that sometimes in developing countries, technological levels are not as high as in Europe, okay, or in other countries, okay. We are just talking about Europe because we are in Europe, okay. So for sure it's an issue, but I think that everybody of us have been looking sometimes at those pictures of landfill sites in which people is getting there to grab something, to get some money, reselling plastic bottles or something like that. So I mean, in these countries, I think that the waste management is also a very important social point, together with an environmental point.
Thank you. Then we have another technical question. This time, I think it will be for Rüdiger. So, what is the flue gas stack temperature from typical waste incineration plant? And are the stacks chimney corrosion protected with some special coating to protect against HCI or H2SO4? I don't think this question will say a lot for everyone. Maybe Rüdiger, I believe someone in the industry is interested in your answer.
Typical temperature is in the range between, let's say, 180 degrees C if you use sodium bicarbonate as an additive, and with 120 to 140 for the condition dry systems, but it can go down to saturation temperature if you have as a large stage wet scrubber system. In that case, typically you have a plastic liner in the stack. For the others, you use the inner tube in the stack with stainless steel or corten, followed by some insulation. There is not so high risk of corrosion due to acid dew point, because the responsible for the acid dew point is SO3, and that is mainly fully absorbed in the processes upstream.
Thank you. I will try to give less technical question, because I think we will lose people then only for a few people in the audience. We have a question: which flue gas cleaning systems are future-proof in the waste-to-energy sector, especially with increasing limit values? I mean, are there some that are not future-proof, I must say? So, who wants to take this question? I think maybe you again, Rüdiger.
I think at the end, it depends on application. All these technologies which I presented, they are not all, there are some more, but the mainly used ones, they are all listed as BAT in the waste incineration breath, and it's more up to the application, how to combine the different technologies. You could see in my presentation, there were some which were a combination of SNCR with, for example, conditioned dry, but were as well more complex ones with conditioned dry, SCR and SNCR. And of course, we have to prepare to the requested emission limit values, and the waste incineration breath gives the range of the maximum values, and we have to follow at the end the permit of the plant.
Thank you.
But it's difficult to say this is the best one and this is for the future. They are all for the future, and it's a combination of technologies.
Mm.
If I can add, maybe just not new technology, but one potential line of intervention to foster PM emission control is double fabric filtration. Typically now we have electrostatic precipitators followed by fabric filtration. In some new plants in Italy, they have installed double fabric filtration, so double stage with that technology.
Thank you. So at the same time, you answer some questions we have about PMs. And now I will come back to Anita, because we have a lot of technical questions, but I want also to ask some questions with regards to policy. Maybe I will start with one of us. What would be the process to define common compliance rules, and how can stakeholders be involved? It's in reference to your recent proposal for the AD.
Yeah, thank you. Yes, we propose to introduce common assessment compliance rules for installations that are covered by Annex 1 of the IED that apply bad conclusions, because in this moment we only have assessment of compliance rule under Chapter 4, Annex 6, and for large combustion plants under another chapter of the IED. But for all other activities, the assessment of compliance rules are not given in Chapter 2 of the IED, and we think in order to achieve the high level, the unique implementation at EU level, so that it will be useful to set assessment of compliance rules for all installations in Chapter 2 in the scope of Annex 1, so that they apply the rules for continuous monitoring of pollutants. But then we have here a specific situation with waste incineration plants, because there are already some rules that are in Annex 6. And we hope that with this new implementing act that will be adopted within 2 years after the revised directive will enter into force, will also solve some discrepancies between these requirements and the new one that then will be proposed for in general for all other activities. So this will be adopted by the comitology procedure. So the Commission will initiate this proposal for the implementing act that will define these new rules, common rules, and then it will be a vote by the by a committee of Article 75 that consists of member states. But of course, we will be happy also to discuss and find a way how to discuss also some ideas with the other stakeholders, including also industry.
Thank you. I'm taking notes at the same time. We have another question for you that is very specific, but since it's addressed to you, I will take the opportunity to forward it as well. I would like to ask a question to Anita Matic. how will simplify permit for livestock waste? Maybe too specific.
Yes, thanks. I saw this question. Yeah, first of all, I think that the question is related probably to animal byproducts and combustion of manure, which is in principle not in the scope of the ID. This is covered by animal byproduct regulation. That is this is under responsibility of DG Sante. So there is a regulation in place that controls combustion of manure from some kind of animal byproducts. And that legislation also sets emission limit values for some such combustion. But about details on permitting, maybe we can contact DG Sante for more details to answer this specific question. So I ask, the question can be forwarded to me by email, and then I can contact colleague in DG Sante for more details about the permitting, because I'm not very much aware of details on this.
Okay, thank you very much. I hope the person in the audience will be able to contact you then. But thank you for the answer already. We have maybe a last question that we can take before wrapping up. Let me find it again. Yes, I think it's something important to answer as well. Maybe for you, Leen, since you're on the side of the operators, what is the procedure in case of breach of emissions of dioxin in France? Is that post-festum reaction or operations on waste energy plants will immediately be stopped due to the incident? How often is it accident situation? Is it possible?
Yeah, I'm rereading the question very quickly.
Yeah, I have a hard time reading it as well. I'm sorry.
Yeah. So if I rightly understand this, well, I will just keep my answer very shortly. If any higher emission levels are measured at the plant, it will be immediately stopped. And of course, taking a look at where the problem lies and find this before operation can continue. But I am not sure if this answered, because they're quite general. The more technical sides on this, I would not know, unfortunately. But I just want to underline that, of course, if we notice, measures are always taken to find the problem and to find a solution for this, because you do not want to pollute the environment in any way. So
we don't just keep going if we see there is a problem. Okay, thank you. So since it was a short answer, I have time now for another question. We are talking a lot about POPs and dioxin and so on, but regarding the current EU agenda, we also sometimes have to mention CO2 emissions. And so we have a question about carbon capture. So maybe this could be a question for Aurélie and for the others as well, if you want to answer. I don't want to do any discrimination. How do you see the addition of carbon capture changing the emissions profiles of waste energy plants? Will there be a need to refurbish existing plants to optimize the plants overall?
Yes, so with the post-combustion capture of CO2, this is a kind of flue gas treatment stage that can be added at the end of the standard flue gas treatment. So that means regarding the flue gas treatment of the plant, I would say there is nothing to change, but of course it can change the profile of the emission, because after this post-combustion capture, you will have no CO2 included, and you could have some slip of amine, for example. But there were a lot of tests done that prove that the slips, for example, for amine, is at very, very low levels, under ppm levels. So I don't think that it will be necessary to add anything on the flue gas treatment stage after carbon capture.
Thank you very much. And we are almost at the end of this event, so I'm sorry we still have a lot of questions we cannot address, but we try to do our best. And of course, I'm sure that if you have more questions, you can also contact the speakers directly. To conclude, I would like to thank the speaker for their participation, their interesting presentations, and also to be here with us to answer the question of the audience. I want also to thank the audience for their attendance. Otherwise, we will not have this event. And we believe this is also for you that we are doing that in order to inform the public about our industry and what we are doing. And I will also thank Paolo Nuvion, who is behind the scene organizing this event, and the entire team of ESWET who made it possible. Thank you very much, everyone, and have a nice day.
Goodbye.
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 Bye.
Thank you. Bye.
Bye.